Swayam Prabha. Digital India. Educated India.
Hi everyone, in the today's class we will be discussing about the properties of T as well as the adjoint of T. Okay, so let us start with a bounded operator T. With this operator we can associate two subspaces, namely the null space of T defined by set of all x in H1 such that Tx is 0. So this is called the null space of T. We can easily show that this is a subspace of H1. In fact, it is closed. We can use the fact that T is continuous, and using that we can show that null space of T is a closed subspace. Linearity of T implies that null space of T is a subspace. And another important subspace is a range space, set of all Tx where x is coming from H1. This is exactly T of H1. It is subset of H2. So this is called the range space of T. So here also, because of T is linear, we can show that it's a subspace of H2. Okay. So since T is bounded, we have concluded that null space of T is closed. But in general, range of the operator need not be closed. For example, range of T need not be closed. We can give some examples to show that range of T need not be closed. So let us look at example. Define D from L2 into L2 by D of x1, x2, x3, so on is x1, x2 by 2, x3 by 3, so on for every xn in L2. We want to show that range is not closed. Claim is not closed. Okay. Now first we show that it is a proper subspace of L2. For example, we have this element 1, 1 by 2, 1 by 3, so on. This is an element in L2 but not range of D. If this is in range of T, if 1, 1 by 2, 1 by 3, so on is in range of D, there exist x as x1, x2, x3, so on in L2 such that the D of x is 1, 1 by 2, 1 by 3, so on. That means we can conclude that x1, x2 by 2, x3 by 3, so on must be equal to 1, 1 by 2, 1 by 3, so on. This implies that x1 is 1, x2 is 1, so on. That means we get this element, but this is not in L2. If this element is in L2 minus, if 1, 1 by 2, 1 by 3, so on, that is in range of D, that should be D of x for some x. So when you compute this, we can get x1 equal to 1, x2 equal to 1, so on, which is a constant sequence which cannot be in L2. So from this we can conclude that range of T is a proper, it's a proper subspace of L2. Next we show that C00 is a subset of range of D. So claim is next claim is C00 is subset of range of D. So let us take one element, let x equal to x1, x2, so on, is an element of C00. Then by the definition of C00, there exists some n or some k such that xn is 0 for all n greater than or equal to k. That means we can say that x is nothing but x1, x2, so on, xk minus 1, xk, and all the remaining components are 0. We want to show that this is in range of D. So that means, can we write this x1, x2, so on, xk minus 1 as D of some y1, y2, y3, so on. This is y1, y2 by 2, y3 by 3, so on. So from this we can conclude that y1 is x1, y2 is 2x2, so on, yk is k times xk, yk plus 1 is 0, and that is yk plus 2, so on. So that means, so yk is nothing but, so d of, therefore we can conclude that d of x1, 2x2, so on, k, xk, and 0 is exactly x1, x2, so on, xk, and remaining 0. So that means C00 is a subset of range of D, but we know that C00 space with the L2 norm is dense in L2 space, hence we can conclude that range of D is dense in L2 space. Okay, so we know that it's a proper subspace which is dense, so it cannot be closed. If range of D is closed, then we can conclude that range of D is L2. But this is not true. This is a contradiction. So therefore range of D is a proper dense subspace of the space L2, and range of D is not closed. So this is an example of an operator which is bounded but range is not closed. But as we have noted earlier, that null space is always closed subspace when the operator is bounded. In fact, in this case, the norm of the operator we can show to be equal to 1. So check that. norm of t is exactly 1. Okay. Now immediately we can ask the question that under what conditions the range of an operator is closed. Question: when is range of t closed for a bounded operator t? So before discussing this result, we need to discuss a few more results. Next we prove the following theorem. Let t be a bounded operator between h1 and h2. Then we have null space of t equal to null space of t star t, and the second one is nothing but range of t closure is null space of t star par. Okay. So proof of 1. So let us take x is in null space of t, then we have tx is 0 and hence t star tx is 0. So we can say that is x is in null space of t star t. So therefore we can say that null space of t is contained in null space of t star t. On the other hand, let us take x is in null space of t star t, then we want to show that tx is 0. So the only equation that connects with t and t star is norm tx square equal to inner product tx with tx. So we can write norm tx square is inner product tx with tx, and this is nothing but inner product t star tx with x, and we know that t star tx is 0, hence tx is 0. This implies that x is in null space of t. So from these two inequalities, these two implications, we can say that from 1 and 2 we can conclude that so we have null space of t equal to null space of t star t. Okay. Now let us look at the second one. So to show, we want to show that range of t closure is null space of t star. Null space of t star bar. So let us take y is in range of t closure. We want to show that y is in null space of t star par. So let us take z is in null space of t star. We want to show that inner product y with z is 0. So since y is in range of t closure, there exists a sequence xn in h1 such that txn converges to y as n tends to infinity. So let us look at inner product y with z. This is nothing but limit txn inner product with z by using the adjoint property. This can be written as limit n tends to infinity inner product xn with t star z, but we know that z is in null space of t star, so t star z is 0. So we have taken y from closure of range of t and shown that y is orthogonal to every element of null space of t star. So this implies that y is in null space of t star, or we can say that range of t closure is contained in null space of t star per. Now to show the other way, so to show null space of t star per is contained in range of t closure, it is enough to show the orthogonal complement of range of t per orthogonal complement of range of t closure is contained in orthogonal complement of null space of t star per. So that is okay. So let us take z is in range of t closure per, but we know that range of t closure per and range of t per same. Then we can say that z is orthogonal to every element of range of t. That means we can say that inner product z with tx is 0 for every x in h1. So this implies that inner t star z inner product with x is 0 for every x in h1. So this shows that t star z is 0 or z is in null space of t star. So this is what we wanted to show. We have taken element from range of t closure per and wanted to show that it is in null space of t star. So we have shown. So from this we can conclude that, so we can say that null space of t star per is contained in range of t closure. This proves the second statement. So we have proved these two statements. Now immediately we can have the following corollary. If we replace t by t star in the above conditions, so let us take t is in b of h1 h2, then we can say that null space of t star is null space of t star, and the second one is range of t star closure is null space of t per. The proof is simple. We can only look at replace t by t star in the earlier theorem, and observe that t double star equal to t. So from this result we get okay. One more important corollary we can make out of this is the following. Let us take t to a bounded operator from h1 into h2. Then we have range of t closure is nothing but range of t star closure, and range of t star closure is range of t star t closure. Again, if you are able to show the condition 1 is true, then we can replace t by t star and use the fact that t double star equal to t to get the condition into proof. So we have range of T closure is null space of T star per. This is by 2 of theorem, and we know that null space of T star and null space of T star are same. So this is by, let us say this is corollary 1. By one of corollary 1. Now we know that null space of an operator per, so this is, let us say, A, null space of A perp is null space of, this is range of by 2 of corollary 1, null space of an operator per is range of adjoint of closure of range of the adjoint. This is range of A star closure. You take A as T star, but we know that A equal to A star in this case. So this is range of A closure, but A is nothing but T star. Okay, so this we are writing, we are defining A as T star. So from this we can conclude that range of T closure is exactly range of T star closure. Now to prove the second one, replace T by T star and use the fact that T double star equal to T. Okay. Now as again one more corollary, we can say that corollary let T be a bounded operator from H1 into H2. Then we have the following. The first one, we can state that T is 1 to 1 or injective if and only if T star T is 1 to 1. That means whenever null space of T is 0, null space of T star T is also 0, because the null spaces are same. This follows from the first statement of the theorem, and second statement says that whenever null space of T star is 0, then range of T closure is full space. So range of T is dense. It says that range of T is dense if and only T star is 1 to 1. Now the third statement is using corollary 1. T star is 1 to 1 if and only if T star is 1 to 1, if and only if T star is 1 to 1. The fourth one is range of T star is dense in this is H1 if and only if T is 1 to 1. So 3 and 4 follows from corollary 1, and by corollary 2, let us call this corollary 2, we can say that this is corollary 3. We can say that range of T is dense. In H1, sorry, H2, if and only if range of T star is dense in H2. Similarly, range of T star dense in H1 if and only range of T star T is dense in H1. Okay, we can get this many important results from the earlier corollaries. Okay, now we can ask the question, when an operator have a closed range? Question. So under what conditions is closed? We have given an example that in general a bounded operator need not have a closed range. Okay, so this can be proved as follows. Let us take T2 a bounded operator from H1 into H2. Then we have the following. Range of T is closed if and only if so we can say that then the following statements are equivalent. The first one is range of T is closed. Second one is there exists a positive number k such that norm Tx is bigger than k times norm x for every x in null space of T perp. This is a statement. Let us try to look at the proof of this one. So let us try to prove 2 implies 1 first. 2 implies 1. So we are given that there exists a constant k which is positive, so that norm Tx is bigger than k times norm x. Okay, let us take an element y in range of T closure. We want to show that y is in range of T. Then there exists a sequence xn in null space of T perp such that Txn converges to y. We can get a sequence xn from H1, but we can write xn as vn plus vn, where vn is coming from null space of T and vn is coming from null space of T perp. So we can actually get write down the sequence which we are getting from null space of T perp. That is enough for our purpose, because whenever we write xn as null space of T and v is in null space of T perp, implies Txn we get as t of vn for every n. Hence we can choose a sequence directly from null space of t perp. So we can replace vn by xn and argue the result. Okay, now so we are given that norm of t xn is greater than k times norm xn for every n in n. So this is by the condition that we are given. So let us say this is condition star. So by star this is true. In fact, for n bigger than m, so we have norm of txn minus txm is bigger than k times norm xn minus xm. So this is by star, because whenever xn is coming from null space of t perp, xn minus xm is also in null space of t perp, still this is true. Now txn is convergent implies txn is Cauchy. So this, from that we can conclude that xn is Cauchy. Since xn is Cauchy in a Hilbert space, null space of t perp, so there exists some x in null space of t perp such that xn converges to x as n tends to infinity. But t is continuous, so as t is continuous, we have txn should converge to tx, but we know that txn converges to y. So we have started y with an element of range of t closure, and we have shown that y is of the form tx, so that is in range of t. So therefore range of t and range of t closure both are same. That means range of t is closed. So we have shown that 2 implies 1. Now to show 1 implies 2, so we want to show that there exists a constant k satisfying the condition in star. So assume that range of t is closed. Okay. Now look at this. So let us write t naught as t restricted to null space of t perp. This is a map from null space of t perp into h2, but we can take, instead of h2 we can take it to be range of t. Now range of t is closed, that is also Hilbert space. So null space of t perp and range of t are both are complete spaces. Now t naught, so clearly we can show that t naught is 1 to 1, because if x is in null space of t perp and t naught x is 0, but t naught x is nothing but tx, this implies tx is 0, then x is in null space of t. So therefore x is in null space of t intersection null space of t perp, that is a 0 space. That means x must be 0. So from this we can say that t naught is 1 to 1, and in fact range of t naught range of t, and that is nothing but t of h1. This is t of null space of t, direct sum null space of t perp, but under t null space of t goes to 0, and this is nothing but t restricted to null space of t per t raised to t of null space of t per. So this is nothing but t naught null space of, and this is nothing but range of t naught. So range of t and range of t naught are same. So since range of t is closed, range of t naught is also closed. So now t naught is a bijection. Therefore t naught is bounded. It's a bounded linear map and bijective. Hence, by the inverse mapping theorem, there exists some, we can say that t naught inverse from range of t to null space of t per t naught per null space of t per is bounded. That means, so there exists k bigger than 0 such that t naught inverse t of x is less than k times norm x, k times norm tx. For all x in null space of t per. So this is nothing but t naught inverse. Whenever x is coming from null space of t per, t naught and t are same. This is less than k times in fact this k naught is nothing but norm of this operator. Okay, so this is nothing but this implies norm of tx is bigger than 1 by k norm x for every x in, okay, and this 1 by k is, let us say, our required constant. So let us say this is gamma. So here we can say this is there is some L, this is L, this is L, so this 1 by L. So norm tx is bigger than or equal to k times norm x for every x in null space of t per, where this k is nothing but 1 by L, which is strictly bigger than 0. So this completes the proof of 1 implies 2. So this is a if and only if condition, that this is a characterization of closed range operators. Okay, next we can ask the question, if range of t is closed, can we say that range of t star is also closed, and what more implication we can get from this result. So we'll be proving those results in the next class. Thank you.